Okay, welcome back. We're going to do one example of functions today to sort of wrap up our previous discussion and really wrap up our last set of topics, right? It's sort of our capstone of the first portion of the class where we were doing simulations and stuff like that. And then we'll introduce all of the different kinds of equations that we can solve. We're going to focus on two for the rest of the class, and we'll probably have time to at least introduce the third. So I want to talk to you about the general structure of that, and then on Wednesday we'll actually start solving those problems. The first thing we're going to do, though, is, like I said, write a function. We're going to need Homework 3's solution, so you might want to go onto Canvas and download Problem 3 Part C, the solutions for that. It's on Canvas in the Homework 3 assignment. It's right up there at the top of Homework 3. But I'll give you a minute or two to go grab those, because we're going to use that for our little wrap-up project here for the first part of the class. For Twitch, that wasn't me. I would not have my phone on during a recording. All right, I'm going to switch over to Excel and sort of outline what we're supposed to do with this last function. And then I'm going to turn you loose for probably about 15 minutes or so to see how much of it you can code up in the remaining part. So let's go over there. And let me make sure that's visible. Yep, it's good to go. So here's what we're going to end up doing, if that's correct. We're going to animate the colliding blocks, which is to get it fairly close to the, is it 3 blue, 1 brown? I always get the, I can never remember if it's 3 brown, 1 blue or whatever. Get it close to the 3 blue, 1 brown video, in the sense that we're going to get it to the point where we can see blocks moving back and forth and colliding. What we did on the homework was just the trajectory, right? And that doesn't really look, it has all the same information as the video, but it doesn't really look the same. We're going to do this partly as a way to illustrate why you might want to use a function. Because one thing that we're going to need for something like this is to draw a box, which in this case is a square. So the way that we're going to think about the square is we're going to try to use what we've already got. And what we've already got is the center. And we're going to represent the center point of that box as a pair of coordinates cx and cy. The cy is just 0, right? It's not moving around in the y-axis at all. But anytime you want to plot something on a grid, you probably need an x and a y. So that part we've already solved for, is the way that the center of the block moves. So what we're going to use functions to do is to say, if I know cx and cy, and I know how big the block is, then I can draw the block knowing only that information. And it's a little bit more convenient if we bundle that process into a function, so that we don't have to change our existing code very much, right? All we need is the center position. We'll define the box as a width of 1, but that'll help make our life a little bit easier. So we're going to call this the width. We'll keep the function a little bit more general than we need to. We'll briefly talk about ways that we could have made it easier. But remember back from, I want to say homework 1 and 2, when we had to draw those stair-stepping operations. Anytime you want to draw a line, you have to give it the 2 points on the line. So if we want to draw a square, we have to draw 4 lines, which are defined by the 4 corners that we have here. So I'll just call these points 1, 2, 3, and 4, just for our internal use. So if we wanted to plot that, what our function would need to output is 2 sets of vectors, one for x and one for y. And those would contain all of the coordinates for those 4 points. So for example, our x vector would have to be the x coordinate of point 1, and then point 2, and then point 3, and then point 4. And then in order to actually close the square, we need to do point 1 again, right? If we only did those, it would just draw a line from 1 to 2, 2 to 3, and 3 to 4, but it wouldn't close that last element. So in order to go back, we need to put x1 back inside of there. And for our y, it's basically the same pattern, but just now we're giving y coordinates. y1, y2, y3, and y4, and then we close it with y1. So that'll draw us a square. All of which comes from knowing cx, cy, and the width, right? Once we know cx, cy, and the width, we can calculate all of those x's that are down there with whatever math is appropriate to you. That's sort of what I'm leaving for you to decide. So our task then is going to come in two parts. The first part is going to be write a function to draw a square. I'm going to put it in quotes to draw a square because the function itself doesn't actually do the drawing. The function will just calculate these vectors x and y that we have here. And then we will pass that to a block function to actually draw it. So if we were to do that, the general syntax is, well, actually, I'm not going to give you the general syntax. The inputs to that have to be two components. So I'm going to tell you what the inputs are, and you'll have to do that. One of the inputs is going to be called center, and the other is going to be called width. The first element of center, so center of 1, is c sub x. Right? That's the x coordinate of the square's center. And similarly, center of 2 is going to be c sub y, which is the y coordinate of the square's center. So center here is also 1 by 2, or you can make it 2 by 1. It wouldn't matter which one it is. But center is coming in as a vector. Width is a scalar. It's just going to be a number. For us, width is going to be 1, but I want you to write the function to handle any width, partly as a way to illustrate the typical way that we write functions is in a general way. It would be weird to say this only makes a 1 by 1 square when it's so easy to say it can make any size square. It just happens to be, for our case, it's going to be a 1 by 1 square. The outputs, it'll be two different vectors. So it'll be the vectors x and y. X will have to be either 1 by 5, or if you want it, the shape doesn't matter. You could also have it 5 by 1. And same for y. And the contents of that x and y, they're both going to be vectors. They should have the coordinates that we described above. So start with 1 and then go to 2 and then 3 and then 4. The math of how to go from center and width over to vectors x and y, I will scroll back up after we switch over, or after I shut up here in a moment. I'll let you figure out the math of how to do that. The second part is to animate the blocks, specifically from homework 3, problem 3, part C. So remember with animation, we can now get rid of the trajectories, i.e. the vectors of position as a function of time. We don't need that anymore, right? When we go to animate something, it's no longer necessary to track the position of the particle at every single moment in time and store them in a giant vector. We only need to know the current position of the square, right? Once we know the current position and we plot it, then we can overwrite that position with the next one, whatever the next one happens to be. We'll need two plot handles. Oh yeah. Quote dash, 2 plot handles. Previously, with our particles bouncing around, we only needed 1, but here those 2 squares are separate because we want to be able to draw them separately. So one of these is going to be plot XA, yeah, let's just say XA and YA. Actually, let's say XAS and YAS, just to remind us, we're trying to plot the square, right? It's not just the center coordinate anymore, we're trying to plot the square. And we'll make the A particle blue and the B particle red. And here, XAS and YAS are the X and Y that we get from the, oh, we need to name that function. Let's call it the make square function. This function that we're going to write up here will be called make square. So make square will take in the center location and the width. It'll output an x and a y vector, and then we pass the x and the y vector into plot, and that will actually draw the square for us. And in order to do that, because we want the two squares to be two separate colors, we're going to have two plot handles, one for the blue, one for the red. So once we've got those updated, then remember the way to update the plot without actually closing it and redrawing it is to use things like ha.xdata. So that's going to be the x vector output from make square. And ha.y data is the y vector output from make square. So we update the position of that square and then assign those vectors to ha.x data and ha.y data, and that changes the location of the square. So I'm going to shut up now till about 3:20. Around 3:20, I'll come back and write the make square function, and at least outline some of what we would need for the animate blocks, and then we'll go to about like 3:30 or so to let you have time to try to code the animation. So for now, these are the two that you need. I will shut up and remind you that this is our drawing. I'll zoom out a little bit. And then we will come back to it in a little bit. Also, if you're on Twitch, I am over on Canvas Chat, so if you have any questions, you can put them over there and I will see them. All right, so for no reason other than it helps me write math, I'm going to make a distinction here between the width that comes into the function and the actual width that I need. Because for me, it's easier to say if I need to go from cy up to one of these y-axes up here, I'm going to define a little w as width divided by 2. Not that there's any reason you have to do that. You can just write width divided by 2 somewhere else. And then similarly, this distance from Cx over to the left or the right, this is again going to be w is equal to width divided by 2. And that's just so I don't have to carry around a bunch of these width divided by 2, width divided by 2, width divided by 2, because they're going to be everywhere. What we're provided is the side length of the box and the center position. So it helps to have that little half in there because it makes our life a little bit easier. So I'm going to have that as my definition over in MATLAB, which I'm going to switch over to now. Make sure that's visible. Yep. So I'm going to need a function. I'll go up to home. I like to just say new script because it's blank, but you can say new function and it'll give you the syntax. This will look like function. Remember, the outputs come first, so we wanted to have an x and a y as our output, and the name of our function is make square, and the inputs we said were center and width. And I always like to finish that with an end, because as we saw with at least local functions, it's nice to have the end on there since it's required for that syntax anyway. I like a little comment too, which is calculate the x and y positions of a square's corners. Just for me, so that when I come back to this function, make square could mean an awful lot of things. So I like to give myself a little reminder of what I'm supposed to be doing. Center is coming in as a 2 by 1 or a 1 by 2. It doesn't really matter. So I'll call the first one Cx, and that's center of 1, and the second one Cy, because that's center of 2. And then I want that little parameter w, and I want that to be width divided by 2. This is just a helper for me. You know, whether or not you saw the math the same way as I did, kind of is up to you. And then whenever I do one of these pattern things of drawing, I like to make a comment of what order I'm going in, so that when I come back to the function, I have an idea of where to go if I'm trying to troubleshoot something. So I should be going in the pattern of lower left to lower right to upper left, and then back again to lower left. It's also a little reminder of, like, why does a square have 5 points when it should only need 4? It's just a reminder that I'm closing that loop. So then we have to calculate x for each one of those. So if I think about where is x on the lower left compared to the center, that would be Cx minus w, the little w. Where is it for the right? Cx plus w. For the upper right, it's still going to be Cx plus w. And then for upper left, it's Cx minus w. And the last one is just always the same as the first one, so it's Cx minus w. This is why I like that little w, because that way I don't have to write width divided by 2 5 times, and that whole thing becomes kind of a long, drawn-out vector. Same idea for y, except it's with cy. So if we want to go to the lower left, that's cy minus w. The lower right is also cy minus w, and then both of the uppers are going to be cy plus w. And then we have to close it, because we need to get back down to the lower left, so that looks the same as the first one, which is cy minus w. So this is a nice illustration of why you might use a function. It really doesn't matter that these may not be called x and y whenever you go to actually use this function in a script. It's just in this tiny world of the function, it's convenient to think of them as x and y's because they're x and y coordinates. So I don't have to kill myself trying to say something like square x and square y to distinguish it from whatever's happening somewhere else. Just within this world, I can say the x's are the points of the corners and the y's are the points of the corners as well. So it's nice to sort of generalize or abstract our thought process here. It makes our code a little bit more readable. And then the center and the width coming in, we just set those to be the ones coming in. So now we need that script from part C which is here. I'll drag this down so we can see everything. I'll keep that function there. A couple of the things that we need to do, because this is an animation, I'm going to get you started on most of the animation and then leave a couple of the details to you. We don't need the vectors anymore. Remember, we're not going to have a vector of data. It's just the current position of XA that gets updated over and over and over again. So we don't need that vector, and there's no we could call that XA of 1, but there's no other XA, so we can just leave XA as XA. Same idea with B. We don't need the vectors anymore. We could leave that as XB of 1. It would mean the same thing. But really, all we just need is B. We have to create the plot initially. Plot. So in order to do that, we have to come up with our squares first. So we would need XA for the square and XB for the square. Or sorry, YA for the square. And those are going to come from our make square function. Make square. The center value that has to go in there, so we get this nice pop-up that says I'm expecting center and a width. The center of our box, the x coordinate is XA, and the y coordinate is 0, and the width is 1. There's all kinds of other ways that you could do that. You could create a variable called center A and define that as XA and 0. But here you can also just pass those directly to the function, and that's perfectly okay. And then to make our plot, we're going to create a handle for it and say plot XAS and YAS and make it blue. So that's our blue square, which is what we call block A. And something similar for B. Right? We need a very similar set of code just for block B, which I will end up making red, but I'm going to finish up the rest of this outline and then let you work on that. The stuff way down on the bottom, we don't need, right? We don't need any of this analysis. We're not plotting trajectories anymore. You'll have to do some mild updating on the collision checks up here. Mild, as I say, it could be misleading to say it's mild. At any rate, we're not storing the position, we're updating the plot. So we don't need this stuff anymore. What we're going to need is something that looks like ha.xdata is equal to a new set of XAS for the square, and ha.ydata is equal to some new set of YA squared. And for both of these, those have to come from something like the same call that we just did before, which is make square. And then same for B, plus a pause. Remember, the pause gives MATLAB time to actually draw it to the display. So we'll go about maybe 5 minutes. We'll say back at 3:34 to finish this. But I will give you till 3:34 to see how much of that you can code up now that we've got make square. Okay, so the first thing I'm going to do is finish up the plot up here at the top. So we've got the A plot, which should be a blue square. Then we need to do the same thing for the red. We're going to need to hold on because we need the squares to show up at the same place. And then I'm just going to copy paste the code that I've got up here and paste it right underneath there. It's the same type of command, and that sort of illustrates why it's nice to have a function to do it. The only difference is what we're calling the inputs and the output. So instead of XA and YA, we've got XB and YB, and we want the center to be XB instead of XA. And then similarly, the plot down here, we don't want the handle to be HA because we're not talking about the A block, but instead HB, and we want to plot the XB and the YB because that is our additional block. So this will be our red square, and that's block B. You know, I should have made it blue because then all the B's would be blue. But anyway, it's too late to fix. It can't be changed. So we'll say hold off. That'll be fine. It'll draw those blocks. I'm just going to fix the axes because we don't want it to reset the axes every time that it tries to plot. We want it to stay constant so that it looks like we're always in the same place. So our X limit, remember the center of the block goes from 0 to 10. And since they have a width of 1, it'll go halfway past the 0 and halfway past the 10. So I'm just going to give us a little bit of breathing room and say go from -1 to 11, just so that we can see the full block as it's going. And similarly, the Y limit, I'm going to say -1 to 1, because it's oscillating along Y is equal to 0. It goes a half above that and a half below that. So I'll give us a little bit of space that sits on there. And then so that the thing actually looks square, because if we try to plot that, MATLAB is going to try to force the axes to, or the aspect ratio to be square. We can say PB aspect, and if I have 2 units in one direction and 12 in the other, I can set this to something like 2 and 12. The 1 is always just along for the ride because it's X, Y, and Z. That will scale it to what we think looks like a square. I will be honest, I always get that wrong. When I was practicing this earlier this morning, before the morning lecture, I had to do that 3, 4, 5 times. Just, I know it has to be something like 2 and 12, but maybe there's a +1, or maybe there's a -1, or maybe it's 12 and 2, or something like that. I usually just try it a few times until I get what I need. So there's our plot. I'm going to add a little bit of a pause here just so that it draws the first time. That'll be a slightly longer pause. You don't need that pause. It'll probably just skip over that and go to the next one, but I'm going to put it on there so that we can see it. And then we have to update the code. Remember, there's no such thing as indexing anymore because everything that we have is just a scalar value, right? We do that trick that doesn't work in algebra, where it does work in computer languages or computer code, where we can just read the old variable on the right and then overwrite that variable on the left. So instead of an XA and an XA new, everything here is just XA. So the way to interpret that is MATLAB will get to line 30 and say, read XA on the right-hand side, add to it this quantity UA times DT, and now just rewrite that as XA, right? Ignore the old value because we don't need it anymore. We're just going to draw something afterwards. Same thing with B. There's no new anymore. It's just XB. We will simply rewrite the old value, so we also don't need to index into it anymore. So this is using that tricky computer style algebra. It's not really algebra. It's just reading stuff on the right and then assigning it to whatever's on the left, and whatever's on the left just happens to be that thing that we read on the right, and so it just gets overwritten with the new value. We're not trying to accumulate this data, right? We're not plotting a trajectory anymore. We're just displaying what it currently is. There's a couple of indices floating around down there in the collision check. We can get rid of those too. And now we have to update the plot. It is ever so convenient when you have a function the way that we have written it there. You can assign those outputs to whatever you want. You can create new variables to them, or you can put them directly inside of a plot. So you can say something like ha.xdata, comma ha.ydata. And that is the output now of our make square function. And what do we give it? We give it the current value of XA and 0, and it's got a width of 1. So that's really convenient, right? We don't have to have those intermediate variables that hold the locations of our square, we can do something like this, where we set it up cleverly in the first place, so that we can access those directly. That only well, it's not only working that way. That works primarily because we originally used the make square. Way back up here, these were the data that came out of the make square, and those were the data that got put into plot. So plot is already sort of primed. It's ready to accept outputs from make square without any modifications to it as we go. That's not like a requirement or anything. It's just super convenient the way that we defined make square, that it just happens to be able to be used in the way that we're using it here. The reason it can be used in that way is because it's outputting the same shape of data every time, so we can just pass it back into plot each time. But you could always do the intermediate step and say something like XAS again, or in this one it's XBS and YBS. Right? You can always do this as well, and it'll still work, except now you're giving it XB and 0 and 1. And then define these separately. So you could say hb.xdata is equal to xbs, and hb.ydata is equal to xys, or sorry, ybs. So these are equivalent. So this code is equivalent to this. And you can use either one. It will have exactly 0 impact on how fast the code runs. Whichever one is clearer to you how it's operating, that would be the key. The computer won't care. It's not going to make it run any faster or slower to have that intermediate variable. But we do need to say something like pause of 0.5. This is allow time to update. Right, the computer just needs enough time to actually go into the drawing and update it. So that's good to go. The only thing I'm going to do that you may or may not have to do is, since I'm not sure if it works, I'm going to reduce the initial number of steps. Actually, this was part C. I don't know how that was. I'm going to reduce the initial number of steps to just 40 in case we've got a problem. We can kind of build it up as we go. Something that you don't have to do primarily because your window will pop up, but I have to do so that people on Twitch can see it, is I have to call figure and dock this window. Because if I don't do that, nobody's going to be able to see it, at least not on Twitch. So let's see what happens when I go to run this. Okay, so we've got something. It appears to be moving, but it looks like, I don't know, 2 lines. So I must have screwed up the PB aspect. If I go down here to PB aspect, the X is actually the long one, right? Not the Y. So this needed to be 12 and this needed to be 2. Because the Y is the shorter of the 2. Like I said, this is not an unfamiliar way for me to code stuff, which is give it your best shot, run it, and see what worked and what didn't, and then go address those elements. So there we go. When I switch that, now I've got something that looks much more like a block. They're moving around. It looks like they bounced a little bit. So we can up the number of runs, because so far that's working okay. So let's go up to 100. Still seems to be doing okay. Okay, right one bounced, left one bounced. There we go. We had a little tiny bounce off of the 2. We can increase the time step. Let's go up to 0.2. If you remember from part D on problem 3, there is a limit to how big of a time step we can take, right, before it starts to kind of screw up our simulation. But 0.2 should be okay. They're not going to collide anywhere in there. And finally, we'll go up to 1,000 here because it seems like everything is going the way that we want it to go. And there we go. We've got our colliding blocks, which is fairly close to what we saw on 3 blue, 1 brown. You could do some more stuff like filling them in and adding text and all kinds of stuff like that. But this is sort of the core of it, right? It's kind of nice to watch. I like it. I dig it. So as we wrap up this part of the course, just take a moment and, I don't know, sort of appreciate, even if you weren't able to code all of that as fast as I just did, which I would be somewhat surprised if you could code it all that fast, because I've done it 3 times, so it's a little bit easier for me when I've done it 3 times. But at the very least, the majority of those should be familiar operations to you, right? Like, oh, I saw those somewhere, maybe it's still a little bit fuzzy, that's fine. But take a moment to appreciate, you more or less know what's going on here, right? There's some little pieces around the edge that are probably still a little fuzzy. With some time, you can figure it out, but that's a pretty decent amount of progress for about 5 weeks worth of MATLAB code, right? You've got a simulation that we saw on YouTube of 2 blocks bouncing around. There's a lot that goes into something like that you may not have had to think of initially, right? All we initially see is just 2 blocks moving back and forth, but the process by which we build all of that up, it's not easy. There's a lot of stuff that sits behind it, so we have made some real progress here. And you know how to do it for the particles too, right? I thought the particle one was pretty cool too. When we animated the like 150 or 1,000 particles or whatever, that was a pretty cool one too. But I also like the blocks. That's a neat one. All right, as nice as that is, and as much as I would like to just watch the blocks keep going, let's wrap it up with our introduction to solving things inside of MATLAB. So, which actually we're going to do the introduction over in Excel, because we're going to take some notes for the last like 6 or 7 minutes worth of class. So I'm going to kill this so that it stops running. This will all be posted too. So if you didn't get yours working, you'll still be able to see it on the lecture. But you know, try and take a few minutes to see if you can get yours to work now that you've seen the solution. Not now, soon. All right, I will rename this our make square. And then let's talk about the different ways that we can do to solve things. I'm going to make a quick little table here for today. So we're going to talk about 4 types of problems. We're going to give them a description, as in like what are we talking about, the function that we would use in Excel, the function that we would use in MATLAB, because we will do a little bit of both, and then a couple of comments about what it is we're trying to do here. Make these a little bit bigger so we can see them. I'm also just going to wrap all that text so that we don't have to worry about that. The general type of problem that we're going to spend the majority of our time on is one that's called root finding, which, if you haven't heard the term root finding before, you've undoubtedly done it. This is usually one equation and one unknown. And the way that you've probably seen this is something like solve for x. You've probably done it algebraically. You know, you rearrange an equation, you calculate whatever the missing variable is, and that's your x value. When we say root finding, we're generally referring to a more complicated form of root finding where it's not possible to just solve for x. And so we'll see some examples of that. Not solve for it analytically, like you can't isolate it in your expression. In Excel, the function we would use for this is called goal-seek, and in MATLAB, it's called f0. As a couple of comments, this needs what's called an initial guess. And the reason it needs that is because the algorithm that it's going to use is iterative. And we've already seen what iterative means. We've done iterations before. It means stuck inside one of these 2 functions, either the goal-seek or the f0, somebody wrote a for loop, or most likely a while loop. But it needs somewhere to get started. Otherwise, it's forced to search an infinite number line, which is hard for most computers to do. If you have multiple solutions, you have to run this multiple times. So these root finding algorithms are not capable of saying, here's all the solutions. They can say, here's the solution that it found that was close to where you guessed the solution ought to be. If there's only one, it'll probably find it. If there's more than one, you'll have to take extra care to find those multiples, and we'll talk about that as we go. There's another style of root finding, which it's the same type of problem. In this case, it's n equations and n unknowns. This is also called a system of nonlinear equations. That's the same idea of root finding solve for x, it's just now you've got x, y, z, right? So it's sort of increasing the complexity. In Excel, the tool we use for this is Solver, and in MATLAB, it's called fsolve. Comments on this one, it needs multiple initial guesses. It's one per variable. And that can be hard. And I'm just going to leave it in bold. It can be very difficult to get initial guesses on these. We're going to leave these till later and focus just on the first one, primarily because when we want to make those guesses, we usually have a physical reason behind those guesses. Like we do it all the time in 113, and the things that we're guessing are things like reactor temperature and composition and pressure. And we can ballpark what those ought to be based on, for example, the inlet, right? The temperature, if the inlet's 500 K, it's probably going to be somewhere around 500 K coming out. It's not going to be a million K coming out. So a lot of those guesses are dictated by the problem itself, which is a little harder to do in the abstract because you don't know what those problems are. Another type of problem I'm just going to generally call a linear algebra problem. It's the same kind of n equations and n unknowns, but this time it's a system of what we call linear equations. In Excel, the thing that we use for this, I believe, is called M inverse. And in MATLAB, it's just the backslash operator. This one we're primarily just going to leave for Math 18. That's your linear algebra class. Algebra. This thing, I can't emphasize how important linear algebra is to a huge amount of behind-the-scenes stuff. So, for example, things like fsolve might use it. Things like the ODE solver that we're going to see in a minute will use it. All kinds of modeling software will use it. Usually what we do when we have a super complicated math problem is simplify it so we can tackle it with linear algebra. So it's everywhere. That's why we have a whole class for it. But that's also why I'm not going to touch on it too much here, because you're going to have a whole class for it. And then the last one that we may get to are ODEs. These are linear systems of ordinary differential equations, or ODEs. You have an entire class for that. So for the most part, we're going to wait for math, 20D is your differential equations class. They're going to go into it there, and also in CENG 113. If you're in the CENG side. But we'll probably get to it here, at least to introduce you to the syntax, because once you've done root finding with F0 and fsolve, the syntax is virtually identical to do ODE solvers, and that way you don't feel like you get hit upside the head when you get into 113 and you've never seen it before. You'll see it more or less follows the same rule. The function for this is called ODE45, or there's lots of other ones. There's like ODE15S, or same idea. There's a bunch of different combinations of numbers and letters that are different ODE solvers. Unfortunately, Excel does not have an option to solve ODEs built in. You have to code the solver yourself, which we are not going to do, because it's fun to do once, and you'll probably do it in Math 20D, but there's no need to reinvent the wheel, and we don't really have time to do that. So if we get to ODEs, which we should, we will only tackle those in MATLAB. We won't do those in Excel. So that's where we're headed. We're going to focus primarily on this one, the one equation, one unknown, follow it up with this one, and then at the end of the quarter, we'll probably talk about ODEs. So that's where we're headed, and we'll pick up right here on Wednesday's class. Just don't forget the midterm is due at 5 p.m., so you got about an hour to get that in. Bye, everybody on Twitch. I will stick around over in Canvas chat, too, if anybody on Twitch has any other questions after lecture. But otherwise, I will see you on Wednesday.